Hey, hi, Leon. Welcome to the class.
Thank you, RP. Thank you, sir. I had to wake up to get ready for it. I don't know, man. It's getting harder and harder to
Yes, yes, it is. The technologies will become more and more concentrated.
right.
That's true.
Yes, sir.
And then everything will come together in the multi-protocol lab.
Yeah, I'm excited, man. I'm not going anywhere. I'm definitely gonna tough it out with you. This is a gold mine of knowledge and wealth. So
Right. And to be
I
honest, just preparing for CCIE actually makes you so much more confident into the technologies. So getting the certification is definitely the goal. But when you are going for that goal, you become so much more efficient in all the technologies that you
right.
start getting better offers just if you are prepared, not even certified yet.
hmm
I
Yes.
have seen so many people like in their CVs they say CCI attempted, and that also puts them into a different league than people who never tried. Because
Right.
that takes a
Exactly.
lot of courage also to even attempt the CCI exam
Absolutely.
and
No,
preparation.
no, hmm Yep. Yep. It's only up from here, basically, as long as we apply this stuff that you teach us.
Right, right. And I think the repetition is the key. So every now and then, all the core technologies you should go through again,
Oh yeah.
switching
I
and
plan
routing.
on
That helps
going
a
through
lot.
them. I plan on going through them all the time. This is lifelong now. I'm
Right,
gonna always be
absolutely.
studying something with this from now on. Absolutely. Well,
Right.
guys are joining, man, so I'm gonna shut up now.
Oh yeah, I think Amara has joined. Hey Amara, welcome to the class.
hmm Yes, sir.
Hey, how you guys doing?
Okay, man. Good to see you, sir.
I need to well.
Good, good, good. How are you?
I'm alright. Thanks for asking, Daniel.
Amara, where are you, sir?
Yeah, I'm in Virginia.
Oh, me too.
Oh, which part?
It was another one of us. I think it was three of us total. But I've been for the most part, I was around Northern Virginia,
I
up
actually live
close
in
to
Northern Virginia,
where at?
Fredericksburg,
I don't know where that's at. I was near Stafford.
Stafford. I know Stafford. Oh yeah,
Yeah.
Stafford is close to Fredericksburg. You don't know Fredericksburg? After Quantico?
Yes, absolutely. That's where I work in Fredericksburg and Richmond and Stafford, Reston,
Okay.
all those little areas. Yeah,
Yeah, I work
man.
in Quantico.
Oh yeah. I do see Quantico. They sign for it off the 95 all the time.
Yeah, the military station.
Montego
hmm
isn't that the FBI or something headquarters there?
hmm
Yeah, I got the FBI quarter in Quantico. And then getting Marine Corps.
Nice. All right, so let's get started. It's already 7 minutes past.
So what do
So
we have today?
today we are going to start our multi-day journey of MPLS, multi-protocol level switching.
Oh, Libel, okay.
Yeah. All right,
Alright.
so let's get started. I'm going to mute you guys for the duration of the presentation. So in case if you have any question, feel free to send me into the chat. And let me share my screen. All right, so let me know in the chat if you guys can see the screen. All right, thanks. Thanks for the confirmation. So let's introduce what is MPLS and how do we configure this. All right, I see a question already from Amara. Do we have VPLS in the CCI exam? So we do have VPLS in CCI service provider, but in CCI routing switching, you only have L3 VPN part of the MPLS. So uh, virtual private LAN services are not part of that, which is because that is part of the L2 VPN, right? Layer 2 VPN. Right. All right. So First of all, let's understand what exactly do we mean by MPLS. And yeah, we do have VRF in this and the MPBGP, multi-protocol BGP, basically. That's what we are going to cover in this. So MPLS or multi-protocol label switching. So we are dealing here with the label switching concept. So first of all, we need to understand what do we mean by label switching, why do we need it, and then of course the how part will become easy once the what and why is clear, right? So label switching basically is a different way of packet forwarding comparing to the traditional IP routing. Now in traditional IP routing, what do? We actually route the packets. In traditional IP routing, we route the packets based on the destination IP address, right? Based on destination IP address. That means you receive a packet, you check the destination IP address into the packet, and you check it against the routing table and see if you have a route for that network, the destination IP, which the destination IP belongs to. And if you do, then you are going to forward the packet to the next hop, and then your duty is done, your job is done, right? That's your traditional IP routing based on the destination IP. But in the label switching, what we do is instead of using packet forwarding based on the destination IP, we actually use labels. So there are some numerical values which are called labels, and these labels are used to decide what will be the next hop. So if a router receives a packet on an interface, and this is an unlabeled packet, means it's a normal packet. In this case, it is going to just simply, if it is an unlabeled packet, it is just going to decide it based on routing table, that where to send it further, right? But if you receive a labeled packet, let me see, the packet has a label also, then you are going to not check the routing table. Instead, you are going to check something called LFIP, label forwarding information base. And this is basically, you can call it the label table, right? But the label table doesn't actually is not used actually as an official term, but just to understand that just like routing table, this is the label table, and it is officially called label forwarding information base, or LFIP. And based on the LFIP also, you will get the same result, that you will find the exit interface and the next hop, right? Exit interface and next hop IP, so that you can forward the packet further. While forwarding the packet further, you are going to swap the label. So actually, you are going to perform a label operation. Basically, one of the label operations will be performed, and then you are going to send it out. Now, what are the label operations that you perform here? You can either push the label, although if you receive a packet with the label, then push operation doesn't apply. Push means that you receive an unlabeled packet and you are pushing a new label. So I'll explain you in which condition that can happen. But if you are receiving a label packet, you can actually swap it. So swap it with another label and then send it further, or you can actually pop the label. So pop basically means removing the label. So pop simply means that you had the packet with the label and now you're sending the packet unlabeled, right? So push, swap, or pop. These are the three operations you can perform. That means either you can receive a packet without the label and you can start using labeling by imposing a label, which is called pushing, or you might receive a packet with the label already and you just swap it with another label before sending it further, which is called the swap operation. And the third operation is you can decide to stop using labels and remove the label and send the packet unlabeled to the next hop, which is called the pop operation, right? So this is what label switching means. Label switching means your packets are going from the source to the destination using multiple hops or multiple routers in the path, and these routers are doing label swapping. So the very first router will perform the pushing. It will push the new label. The very last router may remove the label, pop, but all the intermediate routers will be doing the label swapping, and that is called label switching. You're switching one label to another label and sending the packet further. So what is the benefit of this? Like if I'm using traditional IP routing versus I'm using the label switching, what is the benefit here? So many people actually have a misconception about this. They think that label swapping is faster than the traditional IP routing, but that's a myth. It's actually not. It doesn't actually make your routing faster or anything. On the other hand, you are adding an overhead. you already had a packet with all the information for traditional IP routing. You are adding extra 4 bytes. So every label is actually 4 bytes or 32 bits. You're adding extra 4 bytes, extra overhead to the packet, if anything. So it's not going to make it faster. But what the benefit you get with the label switching is something very, very interesting and very, very useful. And let me explain you that benefit. Think about this. You have router 1 and it is connected to router 2. Router 2 is connected to router 3. And router 3 is connected to router 4. Now let's say that these are service provider routers. So this is a service provider. And these are all the internal provider routers, or simply called the P router, right? And then router 1 is the edge router. So it is the PE router, provider edge router. Let's call it PE1. And this is also a provider edge router, PE2. These are the provider edge routers because they are on the edge of the network, and they will be connecting to the client, the customer edge router. Whatever the customer edge router is, let's say CE1, and this ID will connect to customer edge router as well, CE2. So maybe one branch of the customer is in LA, another branch of the customer is in New York. Then you want to enable communication between them, you want to exchange routes between them, and that's why they are connecting to this service provider, right? Now, in the traditional routing, what will happen if this LA branch has 1000 routes, which it needs to send to the New York branch? So first of all, you are going to advertise these 1000 routes to your provider edge router, right? And you might be using some routing protocol here. Let's call it IGP1, Interior Gateway Protocol 1. It could be a RIP, EIGRP, OSPF, whatever you're using. And service provider itself is using its own IGP. Let's call it IGP2, which is different from the IGP used between the customer and the service provider, right? So let's actually use a different color for the IGP used by the service provider. Let's call it IGP2, right? So just a second. Yeah. So you can see here that if I'm receiving 1000 routes from my customer and I need to send them to the other side, you can see we are not using the same IGP, IGP1 versus IGP2. And even if it is same routing protocol, it will not be the same process ID or same autonomous system number because you don't use the same protocol with the customer. So how do you transport these 1000 routes to the other end? Now, one method could be I can redistribute these routes into my routing protocol, and then it will go to router 2, and router 2 will install them into the routing table, all 1000 routes, and then it can go to router 3. Router 3 will install them into the routing table, all 1000 routes. Then it can go to router 4, but it will go to router 4 in IGP2. So then you redistribute it back into the customer routing protocol, so that ultimately the customer H2 or CE2 will receive all the 1000 routes, right? So yes, technically it is possible. That is something you can do, but you can see that that's not something which will be accepted either by customer or the service provider. Why? Customer will not be happy because its routes are getting leaked into the service provider network. So every router in the service provider network will know about these 1000 routes, and there is no privacy for customer, there is no isolation for customer is saying, okay, I can understand if router 1 needs to keep these routes and router 4 needs to keep these routes for the obvious reason to send it to the C router. But why are you sending it to every other router in service provider network, the P routers like router 2, router 3, and there could be 10 other routers, right? So that is, you're leaking my routes to your organization routers, and I am not comfortable with that. So customer is not happy. Service provider is actually even more not happy because first of all, every single router in service provider network will have to maintain 1000 routes in the routing table. So taking the bandwidth to exchange them and the processing power for every router and the memory of every router to keep all these 1000 routes unnecessarily because you are not going to use them. These are for customer to customer communication. Second problem the service provider will have is that troubleshooting will become so difficult because if there is an issue in the service provider network, is it because some routes which of the customer or some routes of the service provider? Which part has the issue? Where do we see? And if you want to troubleshoot some routes within service provider, you will see all these extra 1000 routes also, which are not even your routes. Third problem is that we are talking about private connections here. So maybe customer, out of these 1000 routes, you are also sending a network X, which is also used by service provider, because these are private networks. Every company can use them individually. So how, if once you redistribute the routes, how do you differentiate between these two network X? They are same, right? So that is another issue. And the last issue, which is the biggest issue, is that what about other customer? Because you are a service provider, you are not just servicing to a single customer, right? You may have more customers, and all of them are also going to send you few routes. One is sending you another 1000 routes, uh, uh, one more is sending you 10,000 routes. So you can see that it is not scalable. So your internal routers, router 2, router 3, and many other routers like this, which are the P routers, just the provider routers, they will be bombarded with this extra information. So many routes, thousands and hundreds of thousands of routes, which they are never going to use, because they will never try to go to the customer. We are just trying to make sure that the customer can go to the customer. CE1 can go to the CE2 and vice versa. We don't want router 2 or router 3 will to ever to go to these locations. So they are getting these routes unnecessarily, just because they needed to forward the traffic in future in the proper direction, right? So your core network, the service provider core network, cannot be free from these customer routes, right? On the P routers, I can understand we need to receive these routes so that we can somehow send them to the other P router. So we need to deliberately use stronger routers here. But all the other internal service provider routers, they are unnecessarily getting all these routes just because, just for the sake of providing reachability. So you can see you had all these issues if you are using traditional IP routing only. Now think about label swapping. How does the label swapping can help in this scenario? So let me clean this up a little bit. So in label swapping, what happens? You are going to form, and let me put it here. You are using some IGP here. Let's say IGP2 between router 1, 2, 3, 4. So they can reach each other already, right? Between router 1, 2, 3, 4. For example, PE to PE, I can ping loopback to loopback thanks to some kind of internal routing protocol I'm using in the service provider network. But then I'm going to configure a BGP session between only the PE routers. So I have a BGP session, and this is going to be IBGP, right? Because internal to the service provider network. So I have, let's say, BGP AS number 100 configured between router 1 and router 4. So router 1 and router 4 are the BGP neighbors. And we know that in IBGP, we can have multi-hop neighbors. It doesn't need to be directly connected because the TTL is 255. Now, in this case, the P routers, these routers, router 2, router 3, and maybe there are 50 other routers like this, they are completely BGP free. They are not configured with BGP. So they will not get any routes which is advertised into BGP update packet. They will forward the packet from one end to another end, but they will not use it. They don't have BGP there, right? Now, we use labeling in the way that we, from router 1, we can tell router 2 that, hey, if you want to come to 1111, which is my loopback, you can use the label X. And router 2 says okay. And when router 2 sends this information to router 3, it says if you want to go to 1111, you can use the label Y. And router 3 will tell to router 4, if you want to go to 1111, you can use the label Z, right? So this way, we have actually sent some label information from one router to another. And similarly, router 4 will also say the same thing to router 3, that, hey, if you want to go to 4444, which is my loopback, you can use the label A. And router 3 will say to router 2 that you can use the label B, 44444. And router 2 will say to router 1, you can use the label C. So now you have actually exchanged the labels. So you can send traffic from router 1 to router 4, PE to PE, loopback to loopback, and that will be label swapped instead of the traditional IP routing. So how it will work is that router 1, when it wants to go to 4444, it will create the packet, right? This is the packet going from 1111 to the 4444 internal to the service provider network. and whatever the data you are sending, right? So this is the packet, but instead of sending this packet, I have this information here, and the information is that I can use the label C if I want to go to 4444. Who told me this? Router 2. So I can use this label and I can send the packet to router 2 with this label because router 2 has informed me about this label. So this is what exactly router 1 is going to do. Router 1 is going to place a label here, label C, and then send the packet to router 2. So this is called push operation. You push the new label on this packet. Now the packet goes to router 2, and because you are not receiving the packet without label, you are receiving it with the label. So you are not going to check the routing table. All you are going to check is the label table, LFIB. And the LFIB will say something like this. So on router 2, the LFIB will say that if I ever receive a packet with label C, I am going to swap it with the label B because that's what I received from router 3 to go to 4444. And because I received it from router 3, I will throw the packet out to router 3. So what router 2 is going to do, as soon as it receives the packet with the label C, it is not even going to check the IP addressing because it doesn't matter. I already know where to send it. I already know which router to send it, right? Because I have the label information in my table. So I receive the packet with label C. I swap it with label B. So this is my packet coming from 1111 going to 4444. And I'm going to swap the label from label C to label B because router 3 send me the label B and throw the packet out toward router 3 without looking at the packet at all. So this operation is called the swap operation because you swap the label C with label B and sent it to router 3. When router 3 receives the packet with a label, it is not going to check the routing table. It is simply going to check the label table, and the router 3 will see this information in the label table that if I receive a packet with B, I will swap it with label A because I had received the label A from router 4 for the network 4444. And I will, because I received it from router 4, I will throw the packet toward router 4, right? So that's exactly what router 3 will do. Router 3 is going to swap this packet label, swap this packet's label from B to A and throw this out toward router 4. This is again a swap operation. So it will keep on happening. You can have 100 routers in the middle between router 1 and router 4, but they will all keep on swapping the label from the incoming label to the outgoing label, incoming label to the outgoing label. And that way, none of the internal routers like router 2, router 3, maybe 50 other routers, none of these routers need to check the packet. None of these routers need to check the routing table. All they need to check the label and then forward the packet in the correct direction. No need to check the payload of that label. And once it reaches to router 4 is going to see this information in the label table that label A has no associated label for the network 4444 because router 4 actually created the label, right? So router 4 is going to receive this packet with the label A. It is going to remove the label because there is no associated label. So router 4 will remove the label and the packet will be exposed here. And this operation is called the pop operation because you are removing the label, right? The label is gone. And once you remove the label, the packet is exposed. And once the packet is exposed, you will have to do the routing lookup and find out how to go to 4444. And you will find out, oh, it's my connected network. So that's the end of the packet journey, right? So this is label swapping. What benefit do you see here? There is one very, very important benefit, as you can see, is that router 2 and router 3, which were the intermediate routers, they never had to check the routing table. They don't need to care what is inside the packet, what is the source IP, what is the destination IP. Technically, even if they don't know about the destination IP in the packet, it will not matter because they know how to swap the label. So you are actually free from checking the routing table. That means your routing table doesn't need to have the information about the routes. You just need to have the information about labels, right? So basically, you can keep your core from free from the customer routes. Now think about this. Once this information is like this, that means once router 1 can ping to router 4 using labels, and router 4 can ping to router 1 using labels. So why don't we use it for something better? Not just pinging, but why don't we use it for exchanging the routes of the customer? using BGP, because you can see that the BGP section is only between the PE routers. So what will happen in that case? I am receiving 1,000 routes from the customer T1. I can send all these 1,000 routes into a BGP update packet to router 4, and that information will go directly to router 4. Router 2 and router 3 will not install it into the routing table, so they will not have the 1,000 routes for the customer. But that's okay, because when the actual traffic will come, that traffic can be labeled, so that router 2 and router 3 do not need to know the underlying network. Let me give you an example. And with that example, it will become very clear how this can help. So let's say get rid of this. All right. So let's say that customer 2 here, CE2, has a network, and CE2 has a network X. Out of these 1,000 routes that you are advertising, you have one network X, which you advertise to router 4. Whatever the IGP you are using, right? You advertise it to router 4. Router 4 advertises it or redistributes it into BGP, not into the IGP that you are using inside your organization, but into the BGP. And we know that only 2 routers are running BGP, the PE routers. So when you redistribute this network X into the BGP, it will be advertised as a BGP update to router 1, and that means router 2 and router 3 will not know about it. They will forward the BGP update packet toward router 1, but they will not see inside the packet because they are not running BGP. So if you check the routing table of router 2 and router 3, it will not have the network X. But router 4 will have it, of course, because coming from the CE2, and router 1 will have it because it received the BGP update. And then router 1 can redistribute it into IGP running towards CE1. And finally, CE1 will receive this network. And CE1 will say, okay, so there is a network X in the New York branch, which I can reach. And if I ever want to go to this network X in the New York branch, I just need to send the traffic or the packets to PE1 router, because that's the one who told me about this network, right? So that's your control plane. Control plane is clear. Just don't configure BGP on your core routers, your P routers, and they will be free of the customer routes. So the same concept can apply to all 10,000, 100,000 routes you have from the customer that can directly go to the other router, other P router. They will not go to the P router. But after that, the interesting point or the labels will be used when you are actually sending the data traffic. How does it work? Let's see an example here after that. So let's say that one of the computers in the LA branch want to go to network X. So the packet is coming from CE1 to the PE1. And the packet is a normal data packet, right? Your CE1 is saying that source is CE1, whatever the network is. Destination is network X. And this could be whatever data, like you're pinging or you're sending some company data. So it's your data packet, not the control packet. When this packet comes to router 1 sees that it is trying to go to network X. Do I know how to go to network X? Yes, because I received an update from router 4 in the form of an IBGP update. So when router 1 checks the routing table, it finds out that network X is reachable via 4444. This is my BGP neighbor, right? So network X is reachable via 4444. Of course, 4444 is not directly connected next hop. So you check again, how do I go to 4444? And that is possible thanks to the IGP you have configured here, some kind of routing protocol like RIP, EIG, RPO, SPF. That's how you can ping loopback to loopback between router 1 and router 4, right? So somehow you will find out that if I want to go to 4444, I need to go to router 2. So the next hop will be, let's say, 12.0.0.2, which is, let's assume that's the IP address of router 2. Next hop. And that's the connected network between router 1 and router 2. So that's the information you have in your routing table, right? Now, this information that 4444 is reachable via router 2, you received it from which router? You received it from router 2, right? Router 2 told you that, hey, I can take you to 4444. And by the way, use the label C, right? That's what router 2 said before, that use the label C if you are trying to send traffic to 4444. So there will be an associated label here, label C. And that's how router 1 will know that I have to start using the label. If you don't have this associated information, you will not be able to send the traffic with the label. So that's why router 1 will not only send it toward router 4 by sending it to router 2, but it is also going to use the label that router 2 has suggested. So it is going to place the label here. So this is the packet coming from CE1 going to network X and whatever the data it is. And you are going to place the label C into the packet. And then you send it to router 2. Now look, think about this. When router 2 receives this packet, does router 2 know about network X of the customer? Router 2 does not know about the network X because this network X is advertised into the BGP update packet. That means only the PE routers know about this route and the 10,000 or 100,000 routes of the customer. Router 2 and router 3 are completely oblivious about these routes. So router 2 definitely doesn't know about this network. And if it had been a normal IP packet, router 2 would have dropped it. But router 2 is receiving something with the label C. And as I told you earlier, router 2 has this label table that if I receive something with C, I swap it with B and throw it toward router 3. So that's exactly what router 2 is going to do. It is going to swap this label. It is going to swap this label to C, sorry, to B. This is your packet. It is going to swap the label to B and send it toward router 3. And the magic of this is you don't need to look inside the packet what is there. All you need to worry about is swapping the correct label and throwing it to the correct direction. You don't need to see inside the packet, so you don't need to have the route in your routing table. That's the benefit of label switching. That means you can have hundreds of thousands of routes from customers, but only your PE routers need to know about them. Thanks to the label swapping, all your internal routers can be BGP free and can be completely customer routes free. So BGP free core and customer routes free core can actually help your service providers to scale to as many customers as they want and as many routes as they want to receive. That's the benefit of label swapping, because internal routers, they just swap the labels, they don't check inside the packet, right? And then router 3 will swap it from B to A and send it to router 4. And that's what you wanted, right? You wanted the traffic to somehow reach router 4. Once router 4 receives it, router 4 is going to check that you are actually not destined for router 4. It is going to network X. But of course, router 4 knows about this network because it has this IGP neighborship with CE2 and is receiving the route right here, right? That's the benefit of label swapping. Is this part clear? Let me know into the comment if you, or on the chat if you have any question about this. But that's the reason or benefit of using label swapping. And there are a few other things. So let's actually clean it up a little bit to understand that. I'm going to clean it up a little bit. All right. So there are some things that you will notice, and something interesting happens here. For example, first thing you will see is that when the packet comes to router 1, the data packet, the packet is unlabeled. So it's a normal packet, right? And router 1 will have to assign the packet or push operation. But how does it do that? So we know that whenever you receive a normal packet without a label, you are going to look the routing table. You are going to do the CEF lookup, right? CEF is the Cisco Express Forwarding. That's the mechanism to take the routing table and copy it into the hardware, which is called the forwarding information base. So basically, you can call it routing lookup, right? CEF lookup or routing lookup. So on router 1, you are going to perform CEF lookup, means you will check the Cisco Express Forwarding table or FIP table, and you will find out that for whatever the network you are going to, you need to send it to router 4, and that means eventually I need to send it to router 2. But router 2 had sent you a label, right? Label C to use. That information is actually linked into the CEF table. So that's where the router 1 will get the hint. Oh, okay. Not only I have to send the packet to router 2, I need to label it also, because label information is inserted in the step table as well. So on router 1, you just need to perform step lookup, because it will have the initial labels as well, and you will start using labels. So now you will send the packet to router 2 with the label C. When router 2 receives the packet, you can see router 2 is receiving it with the label. So it doesn't even need to do the step lookup. All it needs to do is to check the LFIB lookup, or label forwarding information based lookup. And based on that, I find out that C has to be swapped with B. So I will do that, and I will send the packet to router 3 with the label B. So only one lookup is required, which is LFIB lookup. So if you don't have a label, you do a step lookup. If you do have a label, you do LFIB lookup, but only one lookup is needed. Then the packet goes to router 3. Router 3 also receives something with the label. So it is going to swap it with the next label, which is let's say label A. So on router 3 also, you have just performed LFIB lookup, a single lookup, and it will tell you enough information to send it toward router 4. And finally, you send the packet to router 4 with the label B and A. So B is swapped with A, so you send the packet with label A to the router 4. But think about router 4. On router 4, you will check that something is coming with the label. So when something comes with the label, you perform the LFIB lookup. The router 4 will perform the LFIB lookup to find out that A is not mapped to anything, because you had created the label for 4444, right? So you are the end router. So there is no associated label. That means you will have to remove the label, which you do. And when you remove the label, the packet is exposed. And when the packet is exposed, you will have to perform the step lookup also, because now the packet is there, and you have to check how to send this packet to find out whether it is going to really 4444 or is it going to network X of the customer. That information you will find inside the packet. So you have to perform step lookup as well, right? So there is one issue in this scenario. You can see that every router, the first router or all the intermediate routers, they are only performing single lookup, either step lookup or LFIB lookup. Only the last router, the ultimate router, has to perform two lookups. First, LFIB lookup, because you are receiving something with the label, just to find out that I need to remove this label. And if you remove the label, packet gets exposed, and then you will have to perform the step lookup as well. So it looks like a small thing, but if you are receiving millions and millions of packets every second, it could be very detrimenting. It could be very, very cumbersome for the router, or very resource intensive to perform two lookups every single time. So can we do something to change this? We can, and actually that's the default method which is used. To understand this, let's use a cleaner topology so that it makes more sense. And we just concentrate on this concept in this topology. So again, the same thing, we have four routers: router 1, router 2, router 3, and router 4. And router 4 has a loop back here, 4444. So what router 4 is going to do, it is going to advertise this to router 3 saying, hey, if you want to go to 4444, you can use the label, as I mentioned earlier, you can use the label A. And router 3 says to router 2, if you want to go to this network, you can use the label B. And router 2 says to router 1, you can use the label C, as we saw earlier, right? So if the traffic comes to router 1, it will push label C. Router 2 will swap it with label B. Router 3 will swap it with label A. And then router 4 will have to perform two lookups, because first it has to remove the label, and then it has to perform the step lookup. Instead, what happens is, to reduce the number of lookups on router 4, you are not going to send the label A for 4444. You are going to send a special label, which is called POP. So POP means remove the label. So indirectly, you are telling router 3 that, hey, before sending me the packet, please remove the label. You are saying that. And then you can send it to me, to router 4, right? Now what will happen is that when router 1 receives the packet, of course, it receives the packet without label. So it is going to perform the step lookup. And in the CEF table, it will tell you that, hey, you have to go to router 2. And by the way, you have to use the label C. So label information will be there. So router 1 is going to perform push operation, right? And it is going to push the label C and send the packet with the label to router 2. When router 2 receives it, it is going to swap the label from C to B, right? And send it to router 3. So it is performing the swap operation. And on router 3, this is where the interesting thing will happen. You can see that when router 3 receives the packet, and by the way, on router 2, you only perform the LFIB lookup because you received something with the label. So you just need to check the label table or LFIB table. And in the LFIB table, you can find out, or LFIB, you can find out what next label to use. Now, router 3 receives this packet, and router 3 is also receiving it with the label. So, of course, it is going to perform only LFIB lookup, right? And it is going to swap it with what? You can see that on router 3, it says swap the label B with pop. Pop means indirectly saying remove the label. So although router 3 is only performing LFIB lookup, but it knows that I need to remove the label. So router 3 is going to remove the label. And if the label is removed, the packet will be exposed, right? So does it mean router 3 will also have to perform step lookup? No, because you see that pop is actually a label. Unlike having no label, it is actually a label number. It's called label number 3, and the name is pop label. So since it's not the absence of the label, it is a label which has a special meaning. So there is an associated next hop, like router 4, and the next hop IP address exit interface. So although router 3 will remove the label, but it doesn't need to look at the packet. It can directly throw the packet toward router 4 without looking inside it. So router 3 doesn't need to perform one more lookup. Step lookup, LFIB lookup is enough, but it is going to perform the operation of pop, means removing the label. And then only a normal packet will reach to router 4. And of course, if you receive a normal packet, which kind of lookup do you do? Only the routing table lookup, right? Or step lookup. Because you didn't receive any label, so you don't have to check the label lookup. So then you will send it to the correct destination. So you see that we reduce the number of lookups on the last router by popping the label on the second last router. Second last means penultimate router. So penultimate router remove the label before sending it to the ultimate router or router number 4, or pop the label. So this phenomena is called PHP or penultimate hop popping. Penultimate hop popping, which means PHP. So basically the second last router will remove the label instead of the last router. And that's the default method of using MPLS here, right? So that's the benefit of MPLS L3VPN and MPLS labels and label switching. And PHP happens so that nobody has to do more than one lookup. And these are the operations you do: push, and then all the intermediate routers will perform swap until you reach to the second last router or penultimate router. The penultimate router will perform pop, means removing the label, and send the unlabeled packet to the next router, right? So let me know into the comment if it is clear that wide label switching can be beneficial. Label switching can be beneficial to keep your service provider core routers, internal routers, BGP free, and also the customer routes free. They don't need to keep the customer route information at all, because all they will see is label, incoming label, swap it with the outgoing label, and send the packet without looking inside the packet. So all the customer data can travel from one end to another end using or via the routers which do not have the routes. They just have the labels for the PE routers. So basically, you are forwarding the packets to other PE router and asking the intermediate routers to not look into the packet, just look the label which is there to take the packets from one PE to another PE, right? So the question is that which routing protocol or which protocol do we use to create these labels and distribute these labels to each other, like router 1, 2, 3, 4, the service provider network. You can see that we are creating the label A, B, C, or X, Y, Z, and then we are sending them. So which protocol do we use, and what is the structure of this label? So first thing first, the label that we have been talking about is actually a number. It's a 32-bit number. And it's a 32-bit value actually. And And this 32-bit value is actually divided or structured in this manner. So a single label will have the label number for the first 20 bits. First 20 bits is the label number. And then the next 3 bits is called the EXP or experimental bit. The next 3 bits is experimental bit. Next 1 bit is called the BOS bit or bottom of stack. And then the remaining 8 bits is the TTL, time to live. So this is how you have total 32 bits. So the label number itself will be 20 bits. And others are actually have special meanings. Like what is EXP? So EXP or experimental bit this is actually used for the quality of service, QoS. So you can actually have different experimental bits, and accordingly that label will be preferred over other labels. So for preference level of QoS, you can actually use experimental bits, 3 bits. And what is BOS? So BOS is actually stands for bottom of stack, and bottom of stack. And what it means is, it tells you whether it is the last label in the packet or are there more labels to follow. So it's a single bit, right? 1 bit. It could be either 0 or 1. So 0 means there are more labels to follow this label. And 1 means this is the last label. That means after this label, immediately the packet will start. So the reason they need to have this BOS is because you need to understand that packet that you create with the IP addressing and all, that's a layer 3 entity, right? And then the frame is layer 2 entity, the frame, which has the MAC addresses and everything. But MPLS or the labels go here between layer 2 and layer 3. That's why MPLS is also so many times referred as layer 2.5 technology, because it goes between layer 2 and layer 3. And that's where you can place labels. So when you receive a frame, how do you know the frame already has a label and it's not just the layer 2 and then the packet? Because the layer 2 header has the type field, and the type field will have a unique value reserved for MPLS, which will tell you that the next thing is not this packet, but the next thing is the label, right? And that's how you know, okay, next thing is label and I have to read it according to the label structure. But the interesting part is that you can have multiple labels associated with the packet. So you have your layer 2 header, and then you can have label 1, label 2, and label 3, and like this. And then you can have your packet. So if that is the case, the layer 2 header will tell me that the next thing is a label, not a starting of the packet. So that's great. But while I'm reading this label 1, how do I know that after this label we don't have the packet and there is another label? So that's what this BOS tells you. So in the first label, if the BOS bit is 0, that means there are more labels to follow. That's not the bottom of the stack, right? There is more labels to follow. So after this, you again read next 32 bits as the label. And in these next 32 bits, again, you check the BOS value, and that will be 0 again. That means there are more labels to follow. So you know, okay, the packet is not starting after this. There is another label. And now you're reading the last label. And in this last label, you have the bottom of stack bit set to 1. And that means it's the last label. And then you know, okay, after these 32 bits, the packet will start. So this BOS is used to tell you if there are more labels after this current label, or is it the last label, right? If you're wondering why would you want to use more than one labels in a packet, don't worry about it. You will understand it when it comes to L3 VPN, right? Layer 3 VPN implementation of MPLS. Right now, we are just understanding the structure of a label. And TTL is your good old time to live, which simply tells you that how far your labeled packet can go, because every time this number will be decremented by 1, right? So 8 bits means you can go from 0 to 255. Total 256 number, and TTL starts with 255, or it copies it from the internal packet when the label is imposed or pushed. Right. So this is the structure of the label. And now who is creating these labels and who is sending it to your neighbors? Like router 4 is telling to router 3 to use pop label. Router 3 is telling router 2 to use some label B, and router 2 is saying to router 1 is to use label C. So who is the protocol which is taking care of generating these labels and distributing these labels to the neighbor? So the protocol that we use for label distribution is called LDP, label distribution protocol. Label distribution protocol. LDP has only one duty, and that duty is to generate and distribute labels. The question is, so distributing labels is easy. We will have LDP neighbors, means other routers, and we will distribute the labels to them, what labels we have. But we generate the labels for which routes? Only connected routes or any other route? Actually, you generate label for every route you see in the routing table. So an LDP label is generated for every route in the routing table. So an LDP label is generated for every route in the routing table except BGP routes. So if you have BGP LAN routes, you are not going to generate labels for them, because you will see that the BGP has its own mechanism to generate labels. It doesn't depend on LDP. But any other routes you have in your routing table, OSPF LAN routes, EIGRP LAN routes, or any other routing protocol LAN routes, connected routes, static routes, all will have labels generated. One label will be generated for every single network you have in your routing table. Not only connected, but anything even you learn remotely as well. So your LDP label is generated for every route in the routing table except for BGP routes. So once you generate the labels, how do you distribute them and who do you distribute them? So you will see that just like routing protocols, LDP is also configured on the interfaces, and then you can have neighborship with other routers, LDP neighborship. So LDP neighborship is actually is found and maintained in two steps. Step number 1 is called the discovery phase. And discovery phase means you are trying to see if there are any potential neighbors or not on the link, right, on a particular interface. And in the discovery phase, you actually send the LDP hellos, LDP hello messages to LDP hello messages every 5 seconds. And the hold down time, that means how long are you going to wait, is 15 seconds. In the discovery phase, when you did not find the when you haven't find the neighbor yet, that time you are still discovering the neighbor, and then your hellos are rapid every 5 seconds, and you send it to the UDP port number 646. That's the port number used by LDP, source and destination port number 646. But let's say you found a neighbor, a potential neighbor, like you are also configured with LDP and other router is also configured with LDP. You found each other's hellos, discovery hellos over UDP port number 646. And then you think, okay, I can become neighbor with this router. So then it starts the session phase. In the session phase, you are actually going to form the TCP session with your neighbor over port number 646. So this is TCP port number 646, which you will use to form the neighborship. And once you become the neighbor, the hellos are going to be much more relaxed. So hellos will be sent every 60 seconds now, after you found and maintained the neighborship, or found and formed the neighborship. And the hold down time will be 3 times of that. So hold down time will be 180 seconds or 3 minutes. So you are sending rapid hellos on a UDP port only until you find the neighbor on that link. Once you find the neighbor, you form the TCP session over TCP port number 646, and then you start sending hellos to your already established neighborship very slowly, every once in a minute. So every 60 seconds, basically, right? So that's called discovery phase. and session phase. Once your neighborship is up, you're going to advertise all the labels that you generated for every route in the routing table except BGP routes. And the other router will also do the same thing. It will send you the labels for all the routes it knows and whatever the labels it would like to use, right? So what happens is that when you are, let's say, on router 1, and router 1 has a network Z in the routing table. So what router 1 is going to do, first of all, it is going to generate a local label, which is called the in label. And the local label is generated by router 1. So for network Z, I am generating, let's say, label 20. It's just a numerical value, right? Let's say number 20. And then I am going to send this to router 2. Remember, router 2 also have this network Z in the routing table because this is a network from your company and you must be using some IGP like routing protocol. So this network is advertised to everyone. So router 2 also has this network in routing table, and that means router 2 will also generate some label for it. So let's say on router 2, the local label, that means the inbound label generated is 25 for network Z. And you have just received the label 20 from router 1 because you not only generate the label but you distribute it as well. So router 1 will say to router 2, hey, if you want to go to network Z, you can come to me and you can use the label 20 when you come to me. So that becomes my remote label or outgoing label, label number 20. So now if router 2 receives a packet which is going to network Z, and it receives the packet with the label 25 because router 2 is telling everyone to use label 25 to go to network Z. Router 2 will see that something is coming with 25. I will swap it with 20 and send it to router 1. So the packet will be sent to router 1 with the label 20, right? The question is that router 2 will also do the same thing, right? Router 2 will also send this label 25 to everyone, including router 1. Hey, use label 25 to go to network Z. So which information is correct? Whether router 1 should use router 2 to go to network Z, or router 2 should use router 1 to go to network Z. So to decide the best path, LTP doesn't actually use any of its own mechanism. It actually depends on your underlying IGP, whatever the IGP you have configured. So you have to go and check what IGP you configured and what the IGP has to say about network Z, which direction should it go. So let's say router one is connected to router 2, and router 2 is connected to router 3, right? And router 3 is also connected to router 1. Now router 3 has a loopback 3.3.3.3. It is advertising this in OSPF, right? So because OSPF, thanks to OSPF, this network is going to router 2 and to router 1 also from both directions. Let's say the cost of every link is 10. So if you think about router 1, if router 1 has to go to 3.0.0.3, which path will it take? It will take the direct path, right? Because the cost is 10 versus this path which has the cost 20. So router 1 will use the direct path toward router 3, right? Now, with this information, let's say we configure LDP between these routers so that we can start using label swapping. So first of all, they will become LDP neighbors, and then every router will generate the label for every route in the routing table. And of course, 3.0.0.3 is in the routing table of every router, thanks to OSPF. Every router knows about it. So router 3 is going to generate a label for 3.0.0.3, the local label. And the local label is going to be, let's say, for example, 20. Router 2 is going to generate a local label for 3.0.0.3, let's say 25. And router 1 is also going to generate a local label for this 3.0.0.3, let's say 30. Now, router 3 is going to advertise this label to router 2, saying, hey, if you want to go to 3.0.0.3, use the label 20. The router 2 says, okay, thank you. The remote label is 20. Router 3 will also send this information to router 1, saying, hey, if you want to go to 3.0.0.3, use the label 20. And router 1 will say, okay, thank you. The remote label is 20. But router 1 will also receive an LTP message from router 2, saying that, hey, if you want to go to 3.0.0.3, use the label 25, because that's the label router 2 created, right? router 1 will say, okay, I have another label now for the same network Z or network 3.0.0.3. My label is 30, but I receive two remote labels, one via router 3 and one via router 2. So which one am I going to use if I ever receive a packet which wants to go to 3.0.0.3? Will I swap it to 20 or 25? Because I have two remote labels. I could have more than that also if I have other routers. So for that, LDP has no mechanism. LDP says I depend on the underlying routing protocol. I will go and ask OSPF what OSPF thinks. So LDP will go to the OSPF for router 1 and it will ask it, hey, if I want to go to 3.0.0.3, what is the next hop? What do you think is better? And OSPF will say, oh, direct path via router 3 is better. That means the next hop router 3 is better. So this is the label that will go to the label information base or label forwarding information base, right? This is the label that I'm going to use, right? So you may receive multiple labels for the same network from multiple labels, and you are going to keep all of them, all the labels that you receive, you are going to keep them into something called label information base. All the label, like for network 3.0.0.3, label 20, label 25, all you are going to keep in the label information base. But only the best labels goes to the LFIP. And how do I know which labels are best labels? I consult to the underlying IGP, that what do the IGP think, what does the IGP think, which one is the best. So LFIP or label forwarding information base. Label forwarding information base actually contains the information about only the best labels. That means the labels that you are actually going to use for data forwarding. So for example, in lib, I will have this information. 30 is mapped to 20 and 25. 20 is coming from router 3, 25 is coming from router 2. But according to OSPF, the best path to 3.0.0.3 is via router 3. So in LFIB, I will only have this information. Incoming level 30, outgoing level 20 toward router 3. That's the one I'm going to use, right? How do you check the lib or all the labels? You can use the command show MPLS LDP bindings. Show MPLS LDP binding. And if you want to check the LFIP table, you use the command show MPLS forwarding table. Forwarding table, right? But of course, first thing first, how do I configure LDP to have the neighborship, LDP neighborship? And then how do I generate the label? So first, answer to first question, configuring LDP is very easy. That's what I'm going to show you next. To answer your second question, it's even easier. You don't need to generate the labels. Once LDP is configured and it finds the neighbors, it is going to take care of label generation and label distribution. You don't need to do that manually. It is done automatically. You will be able to check your lib and lfib with these commands, and you can also check show MPLS LDP neighbor to see if the neighborship is up. But all you need to do is to activate LDP, and all automatically label swapping will start happening. Just like in the earlier example, after the LDP configuration, router 1 can ping router 4 and the label swapping will happen, and vice versa. They will not communicate without labels, but there will be label swapping happening there, right? So let's take a small break, and after coming back, we will see what commands we can use to configure LDP, right? So few minutes break, and then we'll be back. Yeah, I see your message, Amara. So thanks for the update. I'll see you next week. Hey guys, I'm back. John, Leon, are you guys here? And if you can see the screen, let me know. All right, thanks. Thanks for the confirmation. So how do you configure LDP? This is actually the simplest part of all, because configuration is very easy. Let's say we have few routers, router 1 connected to router 2 is connected to router 3. So let's just take 3 routers for the, or let's say 4 routers so that we can actually check proper level swapping as well. So let's say 4 routers. And the interfaces we have are Ethernet 00 and Ethernet 01. Right? The network that we have between router 1 and router 2 is network 12.0.0.0. Between router 2 and 3 is network 23.0.0.0. Between router 3 and 4, we have network 34.0.0.0. And every router has its own loopback, 1111. Router 2 has loopback 2222. Router 3 is 3.3.3.3. And router 4 is 4.4.4.4, right? So these are the loopbacks. So as I told you that LDP is not a complete routing protocol. It depends on a IGP to find the best level. So we need to configure some IGP here. Now you can decide what you want to use. You want to use static routing, RIP, EIGRP, OSPF, whatever. But the ultimate goal is there should be already reachability loopback to loopback. Everyone should be able to ping everyone else. Now, once that is configured, how do you configure MPLS, LDP? So for LDP, first of all, let's say I'm on router 1. I have two interfaces, loopback 0 and Ethernet 00. So what I do is, first of all, I activate MPLS using the command MPLS IP on the configuration mode. This activate MPLS, and then I need to choose the protocol. So we use the command MPLS label protocol, and there are two options: TDP and LDP. Now you're thinking, what is this TDP? So TDP stands for Tag Distribution Protocol. It was a Cisco proprietary protocol created first, based on which the open standard LDP was created. So MPLS was created back in 2000, but before that, in 1998, Cisco had created something called a Tag Distribution Protocol, or TDP, and using that name tag for the number that we call label. And of course, IEEE said, oh, that looks good. Let me use it and let me create a protocol called MPLS based on LDP. Right. So MPLS is the name of the technology, and the protocol used is called LDP. So nobody now use TDP anymore, because first of all, it's only Cisco proprietary, and second thing is Cisco itself actually recommends to use open standard, which is called LDP. So if you want to use LDP, you will use the command MPLS label protocol LDP. Once the protocol is selected, you want to use a particular router ID. So you are going to say MPLS LDP router ID, and you can mention a local interface which IP address will be used as the unique identification of the router as the router ID. Optionally, you can use the keyword force to change it immediately. If you don't use the keyword force, it is going to change it at the next reboot of the router. So if you don't type the router ID command, it is going to it is going to use the loopback interface as the router ID by default. So it's not required to type this command, but you should know that this command exists. Also, to find the neighbors, it is going to find it using the discovery phase, but you can configure security to configure passwords so that not everybody can become neighbor, and only the routers who have the correct password can become the neighbor. So you can say MPLS LDP neighbor, and then mention the IP address of the neighbor, which should already be reachable, and then you can use the password command, MPLS LDP neighbor password, and then mention the password here. Right. So this is again optional, but you can actually make it secure. After that, you need to activate LDP on the interface. So you go to the interface, let's say interface Ethernet 0/0, and use the command MPLS IP exit. And now LDP is activated, and you will start sending the discovery hellos on the UDP port number 646 on Ethernet 0/0. And if router 2 is also configured, it will also send you the LDP hello messages. They will find each other, and then they will form the TCP session over TCP port number 646, and then your LDP neighborship is up. Right. And the great news is that you don't need to type all this. I told you this so that you know the structure of all the commands, but the only command you need is this one. So if I have a completely blank router, just IP addressing is configured and IGP is configured, then I can just go to Ethernet 00, type MPLS IP, and bang, there you go. You will see that the LDP neighborship is up. How? Because when you type MPLS IP command inside the Ethernet port, it also activates it globally. So you don't need to type this command. Default protocol is LDP. If you don't type this command, so you don't need this command as well. By default, it is going to use the loopback as the router ID. So if you do have a loopback, you don't need to manually change it. So you don't need to type this command. And password is optional. Of course, you should do it, but if you don't do it, it is not going to create any issue. You don't need to type this command. None of these commands are required. Only required command is under interface. You activate MPLS IP, right? Yes. So I see a question from Leon. Does this have to be done on router 2 as well? Yes, and on router 3 as well, and on router 4 as well. On all the interfaces where you can find the potential neighbor. But as I mentioned that these commands outside, they are optional. So you can just do this on every router and you will be good enough. Interestingly, I did not do this on the loopback 0 interface because unlike routing protocol, you don't need to activate LDP on all the interfaces. Then which interface do you activate this on? Only on the interface where you have a potential neighbor. So yes, Ethernet 00 of router 1 is connecting to router 2. So I have to do it there. But let's say on router 2, I have a loopback interface and maybe Ethernet 02, which is going to a computer network where there are multiple computers. I don't need to activate LDP on these two interfaces. I just need it on Ethernet 00 because there is a potential neighbor, and on Ethernet 01 because there is a potential neighbor. Because remember, once LDP is activated, you are going to generate labels for every route in the routing table, which includes your loopback, Ethernet 02, and even routes learned from other routers. You're going to generate labels for everything. So you don't activate this on all interfaces. You activate it only on the interface where you have potential neighbors, right? So just uh, keep doing this on router 1, 2, 3, 4, and the neighborships will come up. You can check it with the command show MPLS LDP neighbor. You can also check show MPLS LDP binding to see the lib table, label information base, which contains all labels. And you can use the command show MPLS forwarding table to check the LFIP, label forwarding information base, which is only the best label that you will use actually to forward the label swapping traffic. And this is found. And how do you know which labels are best labels? IGP helps you in that. So whatever IGP you configured, interior gateway protocol you configure. So whatever interior gateway protocol you configured, OSPF, RIP, IGRP, that will tell you which path is the best path. And that way you can find it out. If you want to see the LDP parameters, you can use the command show MPLS LDP discovery to see the discovery parameters, and that information can be found, right? Going a little bit in more detail, what happens is, let's take router 1, router 2. So when you configure LDP like this, MPLS IP command on Ethernet 00 both routers, first of all, they will choose their router ID. So router 1 will choose 1111, router 2 will choose 2222, because by default, the loopback is the router ID. So the first step that happens is LDP chooses router ID. And generally, it is going to be the loopback interface, unless you change it with the MPLS LDP router ID command, right? If you want to change it, you can do that. But by default, it is the loopback interface. Once the router ID is selected, the same router ID is used as the transport address. By default, the transport address is the router ID. What do I mean by transport address? Means the address which will be used for the TCP session. Remember, I told you that the TCP, the LDP neighborship is over TCP port number 646, and that will happen using the transport addresses, which are by default the router ID of the router. So when you configure LDP, it will start sending the discovery messages, and discovery messages will contain the router ID of the router. And that's how the other router will know, oh, okay, this is where I need to send the TCP SYN message and synchronize message and SYN act and acknowledgement, three-way handshake, and TCP session will come up, right? So let's go ahead and see this in action. So let's go to our lab. And I'm going to use the 4 routers. Let's say router 1, router 2, router 4, router 1, router 2, router 3, and router 5. So we can actually use something like this for this practical. Let's go ahead and start all the nodes. And let's connect to router 1, router 2, router 3, and router 5. Just to show you this example, what I'm going to do is I'm going to, let's actually copy this. I'm going to shut down some of these links so that we can actually check it according to the requirement. So what I'm going to do here is I'm going to shut down these links. So I will not use router 4, and I will shut down the link between router 1 and router 3 so that it is forced to go this way. Router 1 to 2, 2 to 3, 3 to 5, right? So ultimately, this is how it will be: router 1 to router 2, router 2 to router 3, and router 3 to router 5. The networks we know are 12, 23, and 35, which are already configured, right? .1, .2 IP addressing. And we know that the loopbacks are also 1111, 2222, 3333, and 5555. So what I'm going to do first is I'm going to configure some IGP so that they should already be able to ping the loopback to loopback to each other, right? So let's go ahead and do that first. So on router 1, I will shut down the link Ethernet 0/1 and 2. So these links are actually going to router 3 and router 6. So I will have only path to router 2. And on router 2, I will shut down the link serial 1/0 and 1/1 toward router 4. So interface serial 1/0 shut down, and 1/1 shut down, right? And on router 5, I will shut down the link toward router 4 and toward router 8. So Ethernet 0/0/1, interface range Ethernet 0/0 and 0/1 shut down, right? So I'm only using the path according to this: router 1 to router 2, 2 to 3, 3 to 5. Let's go ahead and configure an IGP between these routers. So on router 1, let's say RIP, router RIP version 2 network. I want to advertise my loopback and the network 12 toward router 2. And on router 2, router RIP version 2, router summary, network my loopback, network toward router 2, and network toward router 3. Router 3, same thing, router RIP version 2, no auto summary, network loopback, network toward router 2, and network toward router 5. Finally, on router 5, router RIP version 2, no auto, network my loopback, and toward router 3. You can use OSPF or EIGRP also, perfectly fine. Ultimately, you should be able to ping loopback to loopback. Like if I'm on router 1, I check show IP route, I should see the loopback of router 2, 3, and 5, which I don't see yet because we just configure it. So let's wait for it, and we should see it soon. Yeah, we got the 3 also. Now we should get the 5 soon as well. Because the RIP is slightly slower. Every 30 seconds there's a RIP update, but there you go. I have the loopback of router 5 on router 1. So if I ping 5555 source loopback 0, you can see I have reachability loopback to loopback. And if I do a trace route to 5555, I can see, let's do a numeric. I can see it is going via router 1 to router 2, router 2 to router 3, router 3 to router 5. This is your normal routing, no MPLS configured yet. Now let's go ahead and activate MPLS LDP. How do we do that? Just activate it on the interface going to the other routers. Like on router 1, it should be on Ethernet 00. On router 2, it should be on Ethernet 00 and Ethernet 01. Router 3, Ethernet 01 and serial 1/0. And router 5 will be only serial 1/0, right? I see a question from John. What is the meaning of numeric at the end of the trace route command? So basically what happens is that when you trace route without the numeric command, it is going to try to find the name associated with the every single hop. So like what is the name of 12002? What is the name of 23002? What is the name of 35002? I'm basically trying to find the DNS server to see if there is a name to IP mapping. And of course, we don't have a DNS server, so it is going to just unnecessarily be slow. For example, if I don't use numeric, you see that it is stuck first because it is trying to see if it can find the name of 12002. And if somehow it can find it, it will show you the name also along with the address, right? So then it becomes very slow. And we don't need to see the names, right? So what we do is we use the keyword numeric, and then it becomes very fast. Or if you don't want to use the keyword numeric, you can disable name lookup, no IP domain lookup. When you do no IP domain lookup, now the system will not try to translate any IP to name or name to IP. So now if I do a trace out, it is very fast, just like using the numeric keyword, right? All right. So having said that, let's go ahead and activate LDP. So interface Ethernet 00, MPLS IP on router 2, interface range Ethernet 00 and 1, MPLS IP. See, I'm not doing it on the loopbacks or any other because we don't need that. We just need it on the interfaces where you have potential neighbors. And there you go. LDP neighborship comes up with router 1. And you see the router ID is already selected on router 1, 1111. And router 1, it will show you it is the neighbor of 2222, right? And the TCP session is already up on the port number 646. Let's go to router 3, interface Ethernet 0/1 and interface serial 1/0 toward router 5. Finally, on router 5, interface serial 1/0, MPLS IP, and the neighborship will come. There you go. So everyone has the neighborship. You can check it like on router 2. I have neighborship with router 1 and router 3. So we can check show MPLS LDP neighbor, and it shows you two different parts. One part about the neighbor 1, router 1, and one part about the router 3. So you can see that the neighborship is with this router ID, and my local router ID is this. And the TCP connection, the transport address is also same, because as I told you, transport address is same as the router ID by default. You can change it, but by default it is the same. And I'm using the port number 646. And one of the router will be using the client side port number, so it will be a random port number. Another router will use the TCP port number 646. And it is always going to be the lower number, which will have the port number 646. Like between router 3 and router 2, router 2 has the port number 646, and router 3 is using some random client side port like this, right? And because of this, now I should start creating labels and exchanging labels. So for example, if I'm on router 2, right? So let's take one particular example. Let's think about 5555, right? So for 5555, I will receive two labels, one from router 1 and one from router 3. Why from router 1 also? Because as I told you, you generate label for every route you have in the routing table. And router 1 does have 5555 in the routing table, so it is going to generate the label for it. So router 2 will also generate the label, which will be the local label. So let's say router 2 generated label X for 5555. This is my incoming label. And I received two label Y and label Z from each router respectively, which I'm going to show you into the lib table, which shows all labels, right? And then only the best label will go into the label forwarding information base. And which one will go, Y or Z? For that, we will go to RIP, because RIP is the protocol we have configured, right? RIP version 2. And we will ask as router 2. So router 2 will say, or router 2 will ask, hey, if I want to go to 5555, which one is the better next stop? Should I send traffic to router 1 or to router 3? And RIP will say you have to send traffic to router 3 because that's the direction you have 5555. You can check it into the routing table also. So IP route. If I have to go to 5555, RIP says go to router 3 out Ethernet 01. And that means I'm going to use the label which is coming from router 3, which is the label C. And that will go to the forwarding information base, label forwarding information base, LFIP. So let's see both tables. First of all, the label table with all the labels. So show MPLS LDP binding. And you can see I have binding for every network that I can find. But let's think about 5555. So I have a local label created, label number 17, and I received two different labels from these two routers. From router 1, I received the label 18, and from router 3 also I received the label 18. So you see that the remote labels that you receive, they can be same also. Why? Because different routers are creating them and labels are locally significant. So of course router 1 doesn't check with router 3 first that what you are creating, and I will not create that one. They can create same. On the same router, the local labels will be unique. Like if I am using label 17 for 5555 locally, I will not use the same label for let's say 3333. But the labels coming from other routers, they can be different like this, right? And sorry, they can be same like this. But which one am I going to use? Am I going to send the traffic to router 1 or router 3? As you saw the routing table, RIP says you have to go to router 3. So this one will go to the label forwarding information base. That we can check with the command show MPLS, show MPLS forwarding table. Here I can see that if I want to go to 5555, my local label is 17, and I will swap it with 18 and send it out Ethernet 0/1 toward router 3. So that's what I'm going to do. If I ever receive a packet with the label 17, I will swap it with 18 and throw it toward router 3 without looking inside the packet at all. So now the label swapping will happen, right? And router 2 will advertise its labels to router 1. So if you check router 1, show MPLS forwarding table, directly what we are going to use. So for 5555, see what I received from router 2. The local label that router 2 had generated, 17. That becomes my remote label, right? So what's happening is router 2 generated the label 17 for 5555, and it has advertised it to everyone, to router 3 also. But router 1 thinks that this is the best label also. According to RIP, I need to go to router 2. So I will install it in my forwarding table, that if I want to go to 5555, I will use the label 17 and send the packets to router 2, right? And on router 2, as we saw, it is going to use the label 18. It is going to swap 17 to 18 and send it to router 3. What about router 3? What label router 3 will use? If you remember that router 3 is receiving the label 17 from router 2, saying that, hey, use this label to go to 5555. But RIP says, no, that's not the best path. You should use the label that is coming from router 5 because that's the best path toward 5555. And what label are we receiving from router 5? This is randomly generated numbers, right? Labels. But this one I can guarantee it is going to be the POP label. Why POP label? Because if you remember PHP, the last router always send the POP label for the directly connected networks, so that the penultimate hop or the second last router can remove the label before sending it to router 5. And POP label is also known as implicit null. And you can check this on router 3. That router 3, if I check show MPLS LDP binding, all labels. So for 5555, I am receiving label 17 from router 2, but that's not the best path. So I'm not going to use that. I'm going to use the implicit null, which means POP label from router 5. And that is what I'm going to install into the LFIP, show MPLS forwarding table. And you can see that to go to 5555, I will pop the label. I will receive anything received in the label 18, I will pop it and then send it to out serial 1/0. I will send it out serial 1/0 to router 5. And that's how the packet will reach to router 5 ultimately, right? So if I start pinging from router 1 to 5555, router 1 is going to create the packet and it is going to place the label 17 because that's what you receive from router 2 and send it to router 2. Router 2 is receiving something with 17, it will swap it with 18 and the packet will become like this, 18 and the packet. and then this will be sent to router 3 because 18 we received from router 3. When router 3 receives something with 18, it is going to swap it with pop, means it is going to remove the label, and the packet will be sent to router 5 without any label. And that way, router 5 will only have to perform the SEP lookup, not the LFIB lookup. So let's see this in action. Earlier from router 1, if you remember, if you see, when we were doing the trace route, it was just showing the number of hops. Now it should actually show us these labels also. Label 17 first, then label 18, and then no label, because then you remove the label, right? So 17, 18, and then no label. Let's see. On router 1, trace route again, 5555, numeric. And now you can see that when I'm sending it to router 2, I'm using the MPLS label 17, and experimental bit is 0. We didn't change that. And then the router 2 is swapping it with 18 and sending it to router 3. So it uses label 18. And router 3 swaps it with pop, means remove the label. That's why when it reaches to router 5, you see there is no label. The label has been removed. Now your network is using MPLS or using the label swapping to go from router 1 to router 5 and vice versa, router 5 to router 1. So the benefit you will get is that in future, if you configure router 1 as the PE router and router 5 as the PE router, you can configure BGP between them, skipping router 2 and 3, and they can exchange all the BGP routes, customer routes, without router 2 and router 3 knowing about it. And when the traffic will have to go from one customer location to another one, you can actually do the level swapping. So router 2 and router 3 will correctly send it to the router 5, or router 5 can correctly send it to router 1 without router 2 or router 3 knowing any of the customer routes, right? That's your LDP configuration. So that's how you configure LDP. You can see very simple configuration, just that you need to understand why do we need this and what exactly is this thing. So once the why and what is clear, as you can see, how is very simple, just using the MPLS command. Some other things you can do is, as I mentioned, you can change the router ID if you want. Let's say I want to use my 12001 IP as the router ID. I don't want to use 1111 as the router ID. So you can force it using the command MPLS LDP router ID will be Ethernet 0/0 interface 4. So you can see that the neighborship will go down and then it will come up again because you have changed the router ID. Neighborship is up. But now if you go to router 2 and check the neighborship, so MPLS LDP neighbor, you see that for router 1, my router ID is changed. So router 1's router ID is changed to 12001. So I'm sending the TCP connection also to 12001 because by default the transport address is same as the router ID. So you just send the TCP connection to the same IP, right? So this is one thing you can do. Another thing, as I said, that you can configure authentication like MPLS LDP neighbor is 2.2.2.2 and password, let's say Cisco. And on router 2, MPLS LDP neighbor is 12001 and the password is Cisco. So you can actually configure authentication as well if you need to do that. By the way, the labels that we have been using, you will see that we start using labels from number 16, and in Cisco it uses from 16 to 100,000 by default, right? The label number. Why do we not use anything between 0 to 15? Because these are reserved labels. These have a special meanings and they have a special use cases. For example, label number 0 is actually known as explicit null. Explicit null means you are not using PHP, not using penultimate hop popping. You will not remove the label on the second last router. You will send it all the way to the last router. You might want to do this if you want to retain the experimental bits, which are used for QoS purpose. But the default is label number 3, which means implicit null, also known as the pop label, right? And this means using PHP, popping the label on the second last router. So these are some examples of reserved labels. So you start using it from 16. If you want to change this range, you can do that because you have 2 raised to power 20 total numbers, right? 20 bits. So you can use the command MPLS label range and you can set the minimum and maximum. So I want to start from 100 and go up to 1000. So now router 1 is going to use the labels between 100 to 1000 only, right? Something like this. So you can use configuration like this. All right, one last thing is that between two routers, let's say router 1 and router 2, Ethernet 0/0, IP address is network 12, 12.0.0.1, 12.0.0.2, and we have the loopbacks 1.1.1.1 and 2.2.2.2. If I ask you that after you configure LDP, how the TCP session will be established? What are the endpoints of the TCP session? So you will say the endpoints for the TCP session, or also known as the transport address that you will use for TCP, is by default equal to router ID, right? Transport address by default is equal to router ID. Now, let's say that, and we know router ID is by default the loopback interface. But let's say that we are not advertising loopbacks into the IGP, or maybe we are filtering the loopbacks in the IGP. That means the loopbacks are not reachable. It can happen in the exam, right? Could be one of the requirement where you have to filter the loopback. It should not be advertised to the neighbor. So if that's the case, then your loopbacks are not reachable, right? You cannot ping loopback to loopback because they are being filtered, or you are not advertising them in IGP. So if the loopbacks are not reachable, will there be a different address that will be the router ID? The answer is no. Router ID is always going to be the loopback unless you change it. And because the router IDs do not need to be reachable, they are just a unique identification of the router. So it is still going to use your loopback as the router ID. But now you see that's an issue, because if the loopback is the router ID, that will also be the transport address by default. That means the TCP will try to form the session over loopback to loopback. And because loopback to loopback are not reachable, TCP session will not come up. So your LDP neighborship will not come up, right? That can happen. And if the LDP neighborship is not coming up, the reason is because loopbacks are not reachable, and the loopbacks are the router IDs. And router IDs are by default the transport address. So what is the solution for this? Solution number one, make sure that the loopbacks are reachable. So if loopbacks will be reachable, then your router IDs will be reachable. That means your transport address will be reachable, and TCP session will come up. But maybe in the exam, they have asked you to filter the loopback, or you can't actually activate IGP on the loopback for some other reason. So you can't basically make the loopbacks reachable. So the second solution would be to change the router ID to something else, like we did on router 1, right? We changed the router ID from 1111 to 12.0.0.1. If you do that, and same thing on router 2, you change the router ID to 12.0.0.2, then the router ID will be different, and by default, transport address is the router ID. So transport addresses will become reachable because they will be 12.0.0.1 and 12.0.0.2. So that solution we already saw, changing how to change the router ID, MPLS LDP router ID command. But let's say I don't want to change the router ID. I just want the TCP session to use different IPs. No, don't use router ID for that. That means the transport address should not be equal to router ID. So I can decouple them. I can use a different transport address, but keeping the router ID same, because router IDs do not need to be reachable. I can keep the router ID same, but I can change the transport address only. That is something you can do under the interface. So you go under the particular interface, like Ethernet 00 on router 1, and you can use the command MPLS LDP discovery. So this is the discovery phase, right? You are trying to form the TCP session. MPLS LDP discovery transport address. So you can change the transport address to something else. So either you can mention any address that you have on the router should be reachable, or you can use the keyword interface. So I'm not saying that you need to type the name of the interface. You need to type this keyword interface, interface. When you use the keyword interface, you are saying use the IP address of the interface where you are typing this command to form the TCP session. For example, think about router 3 and router 5. I am on router 3. If I take show MPLS LDP neighbor include TCP, you can see that toward router 5, I'm using the loopback to loopback addresses as the transport addresses, right? TCP connection is over loopback. Why? Because the router IDs are loopback. So if I stop advertising loopback in the RIP protocol, so router RIP and no network 0.0.0.3, let's see, so run router. You can see network 3333 is gone. So from router 5, it should be no longer reachable. So if I check show IP route, yep, 3.0.0.3 is gone. But the router ID of router 3, LDP router ID is still 3.0.0.3, and you will still try to form the neighborship over that. So, there is a TCP hold down time of 180 seconds, so it will take 3 minutes before you can see it. But let's see if we can do a clear MPLS LDP neighbor. And I want to clear the neighborship with router 5. So you can see neighborship is down, and now it will try to form the neighborship again, but router 5 will try it with 3.0.0.3 and 3.3.3.3 is not reachable, right? So that's the issue I was talking about. So what is the solution? One solution is on router 3, I can change the router ID to something which is reachable like 35.0.0.1, and then it will be fine. Or I can change just the transport address, keep the router ID same 3.0.0.3, because that doesn't need to be reachable. So that is something I do under the interface toward router 5, which is serial master 0, MPLS LDP discovery, transport dash address is going to be the interface address of serial master 0, which is 35.0.0.1. Now with this information, the neighborship between router 3 and router 5 should come up soon, right? So if I check show MPLS LDP neighbor, currently we don't have any neighborship, and soon the discovery messages will go, and that should come up. There you go. Neighborship is up, right? Now, if you see that it's still showing that the neighborship with 3.0.0.3 is up, but it is just the router ID. When you go into the detail, showing MPLS LDP neighbor, you can see that although the router ID of router 3 is this, but the transport address, that means I used to form the TCP connection, is 35.0.0.1 because I have changed it on router 3 side, right? So today we have seen that how MPLS work and why label switching can be useful to keep your internal routers BGP free and customer route free. Of course, we haven't seen the practical for that. We have just seen the practical of how do we change from traditional IP routing to label swapping as we have done. And now router 1 to router 5, we are doing the label swapping. So in the next session next week, we are going to talk about how we can configure one of the application of MPLS, which is for L3 VPN, so that the service providers can provide connectivity services to the clients or different customers, right? So that's it for today. And if you have any questions, let me know. Let me allow you guys to unmute. And also let me send you the first lab of LDP. So thanks, guys. Let me know if you have any questions.
Thank you, RP. I'm gonna say good night now. Have a good one, y'all.
All right. Thanks, Leon. Thanks, John.